Hello, and welcome to Sleepy Science by Nem Vita. Whether you're listening at the end of a long day or simply letting your thoughts slow down, this is a place where curiosity unfolds gently. There's nothing you need to solve, nothing you need to remember, and nothing you need to focus on. If you find your attention drifting, that's perfectly fine. Let the words become a soft background, and let your body settle into rest. Allow your breathing to soften, slow down, and become quiet, steady, and easy. I'm glad you're here. The earth cooled slowly. Heat that had been trapped inside the young planet began to escape into space, radiating outward into the cold emptiness surrounding it. This cooling didn't happen all at once. It took millions of years, a span of time so vast that it loses meaning when measured against a human lifetime. The surface, which had been molten and glowing, began to solidify. A thin crust formed, fragile at first, breaking and reforming as the interior heat pushed upward through cracks and weak points. Beneath this early crust, the planet remained hot. Molten rock churned slowly, driven by heat rising from the core. Where this heat found a way through, volcanoes erupted, pouring lava across the surface. The lava spread and cooled, adding to the growing crust. Layer upon layer, the solid surface thickened. What had been an ocean of liquid rock became a patchwork of solid ground, dark and scarred, cooling under a sky that held no oxygen. The first rocks were simple in composition. Basalt formed from the cooling lava, dark and dense, the kind of rock that still makes up the ocean floor today. These early rocks didn't look like the mountains or cliffs we see now. They were flat expanses, broken by cracks, covered in places by fresh lava flows. There were no rivers to carve valleys, no rain to wear the stone smooth. Water existed, but it was in the atmosphere, held as vapor by the heat. As the surface continued to cool, the water vapor began to condense. Clouds formed. Rain fell, perhaps for the first time, striking the hot rock and turning instantly to steam. But the planet kept cooling, and eventually the rain reached the surface without evaporating. It pooled in low places, filling depressions and forming the first bodies of liquid water. These early seas were hot and acidic, nothing like the oceans of today, but they marked a threshold. The planet now had both solid ground and liquid water, two elements that would shape everything that followed. The crust was not uniform. Some areas were thicker, others thinner. Where the crust was thin, the underlying heat could push through more easily, creating zones of volcanic activity. Where it was thick, the surface was more stable. Over time, these thick areas became the foundations of continents, though they were much smaller then. The thinner areas filled with water, becoming ocean basins. The division between land and sea began to take shape. Beneath the surface, the planet's interior was organized into layers. At the center lay the core, a sphere of iron and nickel, incredibly dense and hot. Surrounding the core was the mantle, a thick layer of rock that behaved almost like a very slow-moving fluid. The heat from the core caused the mantle to circulate, rising where it was hottest, cooling as it neared the surface, then sinking back down. This circulation, called convection, was slow beyond imagining. The rock moved at rates measured in centimeters per year, but over millions of years, this movement reshaped the surface. The crust floated on top of the mantle, broken into pieces. These pieces, called tectonic plates, drifted with the slow currents below. Where two plates moved apart, molten rock from the mantle rose to fill the gap, creating new crust. Where two plates collided, one might be forced beneath the other, sinking back into the mantle to be melted and recycled. Where plates slid past each other, the friction caused earthquakes, sudden releases of energy that shook the ground. This movement was the engine that would build mountains, open oceans, and rearrange continents. But in the early Earth, the process was just beginning. The plates were still forming, still finding their boundaries. The surface was unstable, constantly shifting, but the shifts were so gradual that they would have been invisible to any observer watching over the span of years or even centuries. Only when viewed across millions of years did the changes become apparent. The first continents were small. They grew slowly, accreting material at their edges as volcanic activity added new rock and sediments accumulated in shallow seas. These proto-continents were islands, scattered across a global ocean. They drifted, carried by the motion of the plates beneath them, sometimes colliding with each other, sometimes pulling apart. When they collided, the edges crumpled, pushing rock upward to form early mountain ranges. When they pulled apart, the gap filled with water or with new volcanic rock rising from below. Rock, once formed, did not remain unchanged. Water and wind began to wear it down, a process called weathering. Rainwater, slightly acidic from dissolved gases in the atmosphere, seeped into cracks in the rock. When the water froze, it expanded, widening the cracks. Over many cycles of freezing and thawing, rocks split apart. Minerals dissolved in the water, carried away and deposited elsewhere. The solid stone that seemed so permanent was, in fact, slowly breaking down. This broken material, sand and clay and fragments of rock, was carried by water into streams and rivers. The rivers carried it downhill, depositing it in deltas and along coastlines. Over time, these deposits built up in layers. The weight of new material compressed the lower layers, squeezing out water and binding the particles together. Sedimentary rock formed, a record of the material that had been worn away from higher ground. The cycle continued endlessly. Rock formed from molten material, was broken down by weathering, was carried away and deposited, and was compressed into new rock. In places, this new rock was buried so deep that heat and pressure transformed it again, creating metamorphic rock, stone that had been changed but not melted. And in some places, the rock was pushed so deep that it did melt, returning to the molten state and eventually rising to the surface through volcanoes, completing the cycle. The surface of the Earth was never still. It was always changing, always moving, but the changes were so slow that stability was the overwhelming impression. A mountain might take millions of years to rise, and millions more to erode away. A continent might drift across the globe over hundreds of millions of years, moving so slowly that the motion was imperceptible within any individual lifetime. The planet operated on a time scale that dwarfed human experience, where 1,000,000 years was a brief interval. Early in Earth's history, the configuration of continents was nothing like it is today. There was no Atlantic Ocean, no Pacific as we know it. The continents that exist now had not yet formed. Instead, there were smaller landmasses, fragments that would eventually come together and break apart many times over the coming billions of years. The story of the continents is a story of assembly and dispersal, of landmasses colliding to form supercontinents and then rifting apart to scatter across the globe. This process, the Wilson cycle, as it would later be called, repeated itself over and over. It began with a supercontinent, a single massive landmass containing most or all of the planet's continental crust. The interior of this supercontinent was far from the ocean, dry and hot, while the edges were wetter, bordered by shallow seas. Heat from the mantle built up beneath the supercontinent, unable to escape efficiently through the thick crust. Eventually, the buildup of heat caused the supercontinent to dome upward and crack. Rifts formed, valleys that slowly widened as the landmass pulled apart. As the rift widened, seawater flooded in, creating a narrow ocean. The two halves of the supercontinent drifted away from each other, carried by the motion of the plates. Over tens of millions of years, the narrow ocean grew wider, becoming a major ocean basin. Meanwhile, on the far side of the globe, other continents were converging, pushed together by the same forces that had pulled the supercontinent apart. They collided, their edges crumpling to form mountain ranges. Slowly, over hundreds of millions of years, a new supercontinent assembled, gathering the scattered fragments back together. This cycle took an immense amount of time, roughly 400 to 500 million years from the breakup of one supercontinent to the formation of the next. During that time, the face of the Earth changed completely. Oceans opened and closed. Mountains rose and eroded. Climates shifted as continents moved from the equator to the poles and back again. Life, once it appeared, would be profoundly affected by these slow rearrangements, but the planet itself simply continued its ancient rhythms, indifferent to what crawled or swam or flew across its surface. The rocks remember all of this. In their layers, in the orientation of magnetic minerals frozen in place when the rock solidified, in the fossils they contain, the rocks hold a record of the planet's wanderings. By studying this record, it became possible to reconstruct where continents were located hundreds of millions of years ago, to trace their paths across the globe, and to understand that the solid ground beneath our feet has traveled vast distances over deep time. The continents moved, but not in the way that living things move. There was no intention, no direction chosen. The motion was driven by forces deep within the planet, by the slow circulation of hot rock in the mantle. Where hot material rose, it pushed the crust above it upward and sideways. Where cooled material sank, it pulled the crust downward. The plates responded to these pushes and pulls, drifting across the surface at rates measured in centimeters per year, about as fast as a fingernail grows. This seems impossibly slow, and in human terms it is. A person standing on a continent would never feel it moving. There would be no sensation of drift, no landscape sliding past. The ground would seem perfectly still, perfectly stable. And yet, over millions of years, this slow motion carried continents thousands of kilometers. A landmass near the equator could drift to the pole. An ocean basin could widen from a narrow rift to a vast expanse. Mountains could rise where there had been flat ground. The evidence for this motion was not immediately obvious. For most of human history, people assumed the continents were fixed in place. that they had always been where they are now. Maps showed familiar coastlines, and those coastlines seemed permanent. But careful observers began to notice things that didn't quite fit. The eastern coast of South America and the western coast of Africa, for instance, seemed to match, as if they had once been joined and then pulled apart. Fossils of the same species were found on continents now separated by thousands of kilometers of ocean. Rock formations with distinctive characteristics appeared on multiple continents, aligned in ways that made sense only if those continents had once been connected. In the early 20th century, a scientist named Alfred Wegener proposed that the continents had indeed moved, that they had once been part of a single landmass and had since drifted apart. He called this idea continental drift. The evidence he presented was compelling, but he couldn't explain how continents could move through solid rock. Without a mechanism, most scientists rejected the idea. The continents seemed too massive, too solid, to simply plow through the ocean floor. Decades passed. More evidence accumulated. Studies of the ocean floor revealed something unexpected. The floor was not flat and featureless, but marked by long mountain ranges running down the center of ocean basins. These mid-ocean ridges were sites of volcanic activity, where new rock was constantly being formed. The rock closest to the ridge was young, and as you moved away from the ridge, the rock grew progressively older. This suggested that the ocean floor was spreading, moving away from the ridge in both directions. If the ocean floor was spreading, then the continents weren't plowing through solid rock. They were riding on top of plates that included both continental and oceanic crust. The plates themselves were moving, carried by the convection currents in the mantle below. Where plates moved apart, new crust formed at mid-ocean ridges. Where plates collided, one plate could be forced beneath the other, sinking back into the mantle in a process called subduction. This explained how the Earth's surface could be constantly changing without increasing or decreasing in size. New crust formed in some places, old crust was destroyed in others. This theory, called plate tectonics, unified many observations that had seemed unrelated. It explained earthquakes, which occurred mostly along plate boundaries, where the motion of plates created stress and sudden releases of energy. It explained volcanoes, which formed either at mid-ocean ridges, where magma rose to fill the gap between separating plates, or above subduction zones, where the descending plate melted and sent magma back to the surface. It explained mountain ranges, which formed where continental plates collided and crumpled upward, unable to sink into the mantle because continental crust was too light. The theory also explained the distribution of fossils and rock formations. If continents had once been joined, organisms could have lived across the entire landmass, and when the continents split apart, their descendants would be found on now separated landmasses. Rock formations that matched across oceans made sense if those rocks had formed when the continents were adjacent, before they were pulled apart by the opening of a new ocean. The acceptance of plate tectonics transformed geology. It provided a framework for understanding the planet's history, for reconstructing ancient configurations of continents, for predicting where earthquakes and volcanoes were likely to occur. It revealed that the Earth's surface was dynamic, that the seemingly solid ground was part of a system in constant motion, driven by heat left over from the planet's formation and by the decay of radioactive elements deep within the mantle. The motion of plates created different types of boundaries, each with its own characteristics. Divergent boundaries, where plates moved apart, were marked by mid-ocean ridges and rift valleys. The East African Rift is a modern example, a place where the African continent is slowly splitting apart. In millions of years, this rift may widen into a new ocean, separating the eastern edge of Africa from the rest of the continent. For now, it is a valley, dotted with lakes and volcanoes, a place where the Earth's crust is being stretched and thinned. Convergent boundaries, where plates moved toward each other, were more varied. If both plates carried oceanic crust, one would typically subduct beneath the other, creating a deep ocean trench and a chain of volcanic islands. The Mariana Trench, the deepest point in the ocean, formed this way. If one plate carried continental crust and the other oceanic, the denser oceanic plate would subduct beneath the continent, creating coastal mountain ranges and volcanoes. The Andes Mountains formed this way as the oceanic Nazca Plate slid beneath the South American plate. If both plates carried continental crust, neither could easily subduct. Continental crust is too light, too buoyant to sink into the mantle. Instead, the edges of the continents crumpled and folded, pushing rock upward and creating high mountain ranges. The Himalayas formed this way and continue to rise as the Indian plate collides with the Eurasian plate. The collision began about 50 million years ago, when India, which had been an island continent drifting northward, finally reached Eurasia. The impact was slow, but immense. The leading edge of the Indian plate was pushed beneath Eurasia, but the thick continental crust behind it couldn't follow. Instead, it piled up, thickening the crust and lifting the land. The Tibetan Plateau, the highest and largest plateau on Earth, formed from this thickened crust. Transform boundaries, where plates slid past each other horizontally, were sites of intense friction. The San Andreas Fault in California is a transform boundary, where the Pacific Plate slides past the North American Plate. The motion is not smooth. The plates stick together, stress builds up, and then suddenly they slip, releasing the accumulated energy as an earthquake. Over millions of years, this sideways motion has carried parts of California hundreds of kilometers northward. These boundaries, divergent, convergent, and transform, were where most of the action occurred. The interiors of plates, far from the edges, were relatively quiet. Volcanoes and earthquakes were rare. The crust was old and stable. But even in these stable regions, the slow motion of the plates had effects. As a plate moved over a stationary hot spot in the mantle, a plume of hot rock rising from deep below, volcanoes formed on the surface. As the plate continued to move, it carried the volcano away from the hot spot, and a new volcano formed in its place. Over millions of years, this created chains of volcanic islands. The Hawaiian Islands formed this way. The island of Hawaii, the youngest and largest, sits above the hot spot and has active volcanoes. To the northwest, the other Hawaiian islands are older, their volcanoes extinct, carried away from the hot spot by the motion of the Pacific Plate. Even further northwest, underwater mountains mark the locations of even older volcanoes, now eroded below sea level. The chain stretches for thousands of kilometers, a record of the Pacific Plate's movement over the past 70 million years. Hotspots were not fully understood. Unlike the motion of plates, which was driven by mantle convection and could be mapped by studying plate boundaries, hotspots seemed to rise from much deeper, possibly from the boundary between the mantle and the core. They were relatively stationary, or at least moved much more slowly than the plates above them. This made them useful as reference points for tracking plate motion over long periods. The motion of plates was not constant. It varied in speed and direction over time. Plates could accelerate or slow down as conditions in the mantle changed. They could change direction as new rifts opened or old subduction zones closed. Continents could collide, forming a supercontinent, and then remain joined for hundreds of millions of years before rifting apart again. Each cycle of assembly and dispersal was unique, following a similar pattern, but with different details. The oldest rocks on Earth, fragments preserved in stable continental cores, date back more than 4 billion years. These ancient rocks provide glimpses of the early Earth, hints of what conditions were like when the planet was young. But the record is incomplete. Most of the early crust has been recycled, subducted, and melted, its material reused to form new rock. The farther back in time we try to look, the less evidence remains. The continents that existed 4 billion years ago, if they existed at all in any recognizable form, have left almost no trace. But by about 3 billion years ago, stable continental cores, called cratons, had formed. These cratons are the ancient hearts of modern continents, composed of rock that has been at the surface for billions of years. They are surrounded by younger rock, added at the edges through volcanic activity and the collision of island arcs and smaller land masses. Over time, continents grew, accumulating material at their margins, becoming larger and more complex. The assembly of continents from smaller fragments was not a smooth process. It involved collisions, each one creating a mountain range at the suture where two landmasses joined. These ancient mountain ranges have long since eroded, but their roots remain, buried beneath younger rock, detectable through geological surveys. By mapping these sutures, geologists can reconstruct the shape of ancient continents, can see how fragments came together and were later torn apart. The story of the continents is long and complex, a series of cycles stretching back billions of years. Each supercontinent was different, assembled from different pieces in different configurations. But the process that built them was always the same. The slow motion of plates, driven by the heat of the planet's interior, reshaping the surface over unimaginable spans of time. Before Pangaea, there were other supercontinents. The assembly and breakup of land masses had been happening for billions of years, a rhythm embedded in the planet's geology. Each supercontinent left traces in the rock, clues that could be pieced together to reconstruct their shapes and positions. The evidence was fragmentary, more incomplete the farther back in time, but it was enough to show that Pangaea was not unique. It was simply the most recent in a long succession. The oldest supercontinent that geologists have identified with some confidence is called Kenorland. It may have existed around 2.5 billion years ago, though the evidence is sparse and debated. At that time, the Earth was very different. The atmosphere contained little oxygen. Life existed only as single-celled organisms. The continents were smaller, composed mainly of the stable cratons that would later become the cores of larger land masses. Kenorland, if it existed, would have been a collection of these cratons assembled into a single landmass, perhaps surrounded by a vast global ocean. This early supercontinent did not last. Rifts formed, the landmass split apart, and the fragments drifted away from each other. For hundreds of millions of years, the cratons were scattered, separated by oceans. Then, driven by the ongoing motion of tectonic plates, they began to converge again. Around 1.8 billion years ago, a new supercontinent formed. This one has been called Nuna, or Columbia. It gathered together most of the continental crust that existed at the time, creating a large land mass that persisted for several 100 million years. The interior of Nuna would have been a harsh place. Far from the moderating influence of the ocean, temperatures would have swung between extremes. There were no plants to stabilize the soil, no roots to hold the ground in place. Rain fell on bare rock and ran off quickly, carving channels and carrying sediment to the edges of the continent. The land was empty of visible life, though microbes clung to damp surfaces and lived in shallow waters near the coasts. Nuna eventually broke apart, as all supercontinents do. The breakup was gradual, beginning with rifts that slowly widened into ocean basins. By 1.3 billion years ago, the continents were once again scattered, drifting across the globe on their separate tectonic plates. This dispersed phase lasted for hundreds of millions of years. During this time, the continents were smaller and more isolated, separated by wide oceans. The planet's geography was fragmented, with no single dominant landmass. But the cycle continued. The scattered continents began to converge again. Around 1 billion years ago, they assembled into another supercontinent, called Rodinia. This was a massive landmass, perhaps the largest supercontinent in Earth's history, in terms of the proportion of continental crust it contained. Rodinia's configuration is still being worked out, but it seems to have been oriented differently than later supercontinents, with land masses that are now far apart, positioned close together. Rodinia endured for a long time, perhaps as much as 250 million years. During this period, the planet underwent significant changes. Life, still microscopic, continued to evolve. Photosynthetic organisms had been producing oxygen for over 1 billion years, and oxygen levels in the atmosphere were slowly rising. The increased oxygen began to affect the chemistry of the oceans and atmosphere, setting the stage for more complex life to eventually emerge. Around 750 million years ago, Rodinia began to break apart. The rifting process was extended, with multiple rift zones opening across the supercontinent. As the landmass fragmented, the pieces drifted into new configurations. This breakup coincided with a period of extreme cold, when ice sheets advanced far from the poles, possibly covering much of the planet's surface. This was one of several snowball Earth events, times when the Earth's climate cooled dramatically. The exact cause is still debated, but the breakup of Rodinia may have played a role, altering ocean currents and affecting the distribution of heat around the planet. The fragmented continents drifted for a time, scattered across a partially frozen ocean. Then, as the cycle dictated, they began to converge again. By around 600 million years ago, some of the fragments were colliding, assembling into a new configuration. This new supercontinent, called Pannotia, was smaller than Rodinia and shorter-lived. It existed for perhaps 100 million years before it too began to rift apart. The breakup of Pannotia was the prelude to a new phase in Earth's history. As the continents separated, the climate warmed, the ice sheets retreated, and conditions became more favorable for life. Around this time, complex multicellular organisms began to appear in the fossil record. The Ediacaran biota, strange soft-bodied creatures unlike anything alive today, left impressions in rocks from this period. They were followed by the Cambrian explosion, a rapid diversification of animal life that filled the oceans with new forms. The continents continued to drift. After the breakup of Pannotia, the fragments moved into new positions. Some remained close together, others separated by widening oceans. The configuration was complex, with multiple smaller continents rather than a single dominant landmass. This fragmented geography persisted for over 100 million years. During this time, life diversified in the oceans, and eventually, plants and animals began to colonize the land. Around 450 million years ago, the continents began to converge once more. The process was slow, driven by the subduction of oceanic crust and the closing of ocean basins. Two large land masses, Laurentia and Baltica, collided, forming a single continent called Euramerica, or Laurussia. This collision created a mountain range, the remnants of which can still be seen in the Appalachian Mountains of North America and the Caledonian Mountains of Scotland and Scandinavia. These mountain ranges, now worn down by hundreds of millions of years of erosion, were once as tall as the Himalayas. Another large landmass, Gondwana, remained separate for a time. Gondwana was a massive continent in the southern hemisphere, composed of what would later become South America, Africa, Antarctica, Australia, and India, along with smaller fragments. It had formed from the assembly of several smaller continents during the previous cycles and had remained relatively intact through the breakup of Pannotia. Gondwana and Laurussia drifted toward each other. Between them lay an ocean called the Rake Ocean. As the continents converged, the ocean began to close. Subduction zones formed at the ocean's edges, consuming the oceanic crust and pulling the continents together. This process took over 100 million years. Slowly, inexorably, the gap narrowed. Around 300 million years ago, the continents finally collided. The impact was immense, though it unfolded over millions of years. The collision created the Appalachian Mountains in North America, the Variscan Mountains in Europe, and the Ouachita Mountains in North America. These ranges were part of a continuous mountain belt that stretched for thousands of kilometers, marking the suture where the continents had joined. With this collision, the supercontinent Pangaea was born. It was not the first supercontinent, nor would it be the last, but it was the most recent and the best understood. Pangaea brought together nearly all of the Earth's continental crust into a single, massive landmass. Only a few small fragments remained separate, scattered across the global ocean that surrounded Pangaea, an ocean called Panthalassa. Pangaea's shape was roughly C-shaped, with a large embayment on its eastern side called the Tethys Sea. This was a tropical ocean, warm and shallow in places, that separated the northern and southern parts of the supercontinent. The northern part, called Laurasia, included what would become North America, Europe, and much of Asia. The southern part, Gondwana, included South America, Africa, Antarctica, Australia, and India. The formation of Pangaea had profound effects on the planet. With so much land concentrated in one place, ocean currents were disrupted. The climate became more extreme. The interior of the supercontinent, far from any ocean, was dry and hot, a vast desert that stretched for thousands of kilometers. Seasonal temperature swings were severe. Coastal areas were wetter, but even there, the climate was different from what had existed when the continents were more dispersed. Life had to adapt to these new conditions. Many species went extinct during the assembly of Pangaea, unable to cope with the changing environment. But others thrived, and new species evolved to fill the available niches. Forests spread across the wetter regions, dominated by plants like ferns and early seed plants. Animals, including early reptiles and amphibians, moved across the supercontinent, no longer separated by oceans. This allowed for the mixing of species that had evolved in isolation, creating new ecosystems. The rocks from this period tell the story. Sedimentary layers laid down during the assembly of Pangaea contain fossils of similar species on continents that are now widely separated. Coal deposits, formed from the remains of vast swamp forests, are found in regions that were once near the equator but are now far to the north or south, carried there by the subsequent breakup and drift of the continents. Red sandstones, formed in desert environments, mark the dry interior of the supercontinent. Pangaea represented the culmination of hundreds of millions of years of continental drift, the gathering together of fragments that had been scattered and reassembled multiple times over the planet's long history. But like all supercontinents before it, Pangaea was not permanent. The forces that had brought the continents together would eventually pull them apart again, continuing the ancient cycle. Pangaea did not break apart immediately after it formed. For a time, it remained intact, a single massive landmass dominating the planet's surface. Life continued to evolve and spread across the supercontinent. Forests grew where there was sufficient rainfall. Deserts expanded in the interior. Animals moved freely across the land, unrestricted by ocean barriers. The world was connected in a way it had not been for hundreds of millions of years, and would not be again. But beneath the surface, forces were already at work that would eventually tear the supercontinent apart. Heat continued to rise from the Earth's mantle, and with so much continental crust concentrated in one place, that heat had difficulty escaping. It built up beneath Pangaea, warming the rock, making it more buoyant. The supercontinent began to dome upward slightly, creating stresses in the crust. Cracks formed, small at first, running through the rock in long lines. These cracks were the beginning of rifts. They appeared in several places across Pangaea, zones where the crust was being stretched and pulled apart. Not all of these rifts would succeed in splitting the continent. Some would open for a time, and then stop, leaving behind long valleys that never widened into oceans. But others would continue, deepening and widening over millions of years, eventually separating entire land masses. The first major rift began to open around 200 million years ago in the region between what would become North America and Africa. This rift ran roughly north to south, following a line of weakness in the crust. As the rift widened, the land on either side slowly pulled apart. The crust stretched and thinned. Magma from the mantle rose into the gap, solidifying to form new rock. Volcanoes appeared along the rift, erupting periodically as the tectonic forces continued. The opening of the rift was slow. Over millions of years, the gap widened from a narrow valley into a broader basin. Seawater from the surrounding Panthalassa Ocean began to seep into the low areas, flooding the rift. At first, these were isolated arms of the sea, narrow and shallow. But as the rift continued to widen, the seawater advanced further, creating a long, narrow ocean. This was the beginning of the Atlantic Ocean, though it would take many more millions of years for it to reach anything like its current size. The separation was not uniform. The rift opened faster in some places than others, creating an irregular coastline. Where the rift slowed or stalled, land bridges persisted for a time, allowing animals and plants to continue crossing between the separating land masses. But eventually, these bridges sank beneath the rising water, and the continents were fully separated. What had been a single land mass was now divided, with an ocean growing between the pieces. As North America and Africa drifted apart, other parts of Pangaea were also beginning to rift. To the south, Gondwana started to fragment. The first separation occurred between Africa and Antarctica, with a rift opening in the region that would eventually become the Indian Ocean. This rift, too, widened slowly, over tens of millions of years, as the continents on either side moved away from each other. India, which had been part of Gondwana, began its long journey northward. It was an island continent for a time, surrounded by ocean, drifting across the Tethys Sea toward the southern coast of Asia. This journey would take over 100 million years, and when India finally collided with Asia, the impact would create the Himalayas. But that was still far in the future. For now, India was simply moving, carried by the tectonic plate beneath it, slowly crossing the vast ocean. South America also began to separate from Africa, another rift opening along a line that would become the Southern Atlantic Ocean. This separation happened somewhat later than the Northern Atlantic, but it followed the same pattern. The rift widened, seawater flooded in, and the two continents drifted apart. The fit between the coastlines of South America and Africa is one of the most obvious pieces of evidence for continental drift. If you could push the continents back together, they would match almost perfectly, like pieces of a puzzle. Antarctica remained connected to Australia for a time, but eventually they too separated, a rift opening between them and widening into ocean. Australia drifted northward, while Antarctica moved southward, eventually settling over the South Pole. The movement of Antarctica to the pole had significant effects on the global climate. Once positioned there, ice began to accumulate, forming the vast ice sheets that cover the continent today. The presence of a large ice mass at the pole altered ocean currents and atmospheric circulation, cooling the entire planet. The breakup of Pangaea was not a single event, but a series of separations that unfolded over more than 150 million years. Each rift followed its own timeline, influenced by the local geology and the forces acting on that particular region. Some rifts opened quickly, geologically speaking, while others took much longer. Some succeeded in completely separating land masses, while others failed, leaving behind scars in the crust, but no new ocean. The rifting process created new coastlines, thousands of kilometers of them. These coasts were geologically active, with volcanoes and earthquakes common in the early stages as the crust adjusted to the stresses of rifting. Over time, as the rifts widened and the continents moved further apart, the activity diminished. The coastlines became passive margins, stable edges where the continent met the ocean without significant tectonic activity. Along these passive margins, sediments accumulated. Rivers carried material eroded from the interior of the continents and deposited it along the coasts. These sediments built up in thick layers, creating continental shelves, broad, shallow platforms extending out from the shore. The shelves were submerged, covered by shallow seawater, and they became habitats for marine life. Over millions of years, the accumulated sediments were compressed into sedimentary rock, preserving a record of the material that had washed off the continents. The opening of new oceans also created new oceanic crust. At the mid-ocean ridges, where the continents had pulled apart, magma rose continuously from the mantle, solidifying to form new seafloor. This new crust was hot and buoyant, sitting relatively high. As it moved away from the ridge, it cooled and contracted, sinking lower. The oldest oceanic crust, far from the ridges, was the coldest and deepest. Eventually, when it reached a subduction zone, it would sink back into the mantle, completing the cycle. The Atlantic Ocean grew steadily, widening at a rate of a few centimeters per year. This is roughly the rate at which fingernails grow, a pace that seems trivial, but adds up over geologic time. In a million years, a rift widening at 2 centimeters per year would grow by 20 kilometers. In 10 million years, 200 kilometers. In 100 million years, 2,000 kilometers. The Atlantic is now over 6,000 kilometers wide in places, the result of more than 150 million years of steady spreading. As the Atlantic opened, the Pacific Ocean, which had been the dominant ocean during the time of Pangaea, began to shrink. The Pacific is surrounded by subduction zones, places where oceanic crust is sinking back into the mantle. This is why the Pacific has a ring of fire, a belt of volcanoes and earthquakes encircling the ocean. As the Atlantic and Indian Oceans grew, the Pacific was consumed from the edges, its seafloor subducted beneath the surrounding continents. This is part of the Wilson cycle, the opening and closing of ocean basins. While the Atlantic was opening, a young ocean in the early stages of the cycle, the Pacific was closing, an old ocean in the late stages. Eventually, if the cycle continues, the Pacific could close entirely, bringing the continents around it into collision and forming a new supercontinent. But that is tens or hundreds of millions of years in the future, and it may not happen at all. The future configuration of the continents is uncertain, dependent on forces and processes that are still unfolding. During the breakup of Pangaea, the climate changed significantly. With the continents dispersed rather than concentrated, ocean currents could flow more freely, distributing heat more evenly around the planet. The extreme continental interior, the vast dry region that had characterized Pangaea, was broken up. The fragments of the supercontinent each had more coastline relative to their area, which meant more moderate climates, more rainfall, and less extreme temperature variation. These changes affected life profoundly. New habitats appeared as the continents separated and coastlines lengthened. Isolated populations evolved independently, no longer able to mix with their relatives on other land masses. This drove diversification, the evolution of new species adapted to local conditions. Over millions of years, the fauna and flora of the separating continents became increasingly distinct. The breakup also created opportunities. Shallow seas formed between rifting continents, warm and rich in nutrients, ideal for marine life. Coral reefs expanded, fish diversified. Marine reptiles, which had evolved during the time of Pangaea, spread through the new oceans, adapting to different environments. On land, dinosaurs continued to dominate, but they too diversified, with different groups evolving on different continents as the land masses separated. By about 65 million years ago, the continents were approaching their modern positions, though they were not yet exactly where they are today. The Atlantic was wide, though still narrower than it is now. India was closing in on Asia, but had not yet collided. Australia was still close to Antarctica. The geography was recognizable as a precursor to the modern world, but the details were different. The forces that had broken Pangaea apart had not stopped. The continents continued to drift, carried by the motion of tectonic plates. The Atlantic continued to widen. India collided with Asia, beginning the uplift of the Himalayas. Australia separated from Antarctica and drifted northward. Africa moved north, closing the Tethys Sea and eventually colliding with Europe, creating the Alps. Each of these movements was slow but relentless, reshaping the planet's surface bit by bit. The breakup of Pangaea was not a singular event with a clear ending. It was a process, one that is still ongoing. The Atlantic is still widening at the same slow pace it has maintained for over 100 million years. New rifts are opening, like the East African Rift, which may eventually split Africa into two separate continents. The Pacific is still shrinking, its edges still subducting beneath the surrounding land masses. The planet's surface is still in motion, still driven by the same forces that tore Pangaea apart. Mountains rise, but they do not rise forever. The same forces that push rock upward are met by other forces that wear it down. Wind, water, ice, and even the simple passage of time work against the heights, grain by grain, slowly reducing what was once tall to something lower. This is erosion, a process as fundamental to the shaping of the Earth's surface as the tectonic forces that build mountains in the first place. When two continental plates collide, the crust between them crumples and folds. Rock that was once horizontal is tilted, twisted, pushed upward. The collision doesn't happen all at once. It unfolds over millions of years, with the edges of the continents grinding against each other, compressing the rock between them. The pressure is immense, enough to transform the rock itself. Heat and pressure deep below the surface change the mineral structure, turning sedimentary rock into metamorphic rock, harder and denser than before. As the rock is pushed upward, it rises above sea level, forming mountains. These mountains are not finished products, appearing suddenly in their final form. They grow slowly, lifted by the ongoing collision of the plates beneath them. At the same time, from the moment they begin to rise, erosion begins to wear them down. Rain falls on the peaks, seeping into cracks and crevices. When the water freezes, it expands, widening the cracks, splitting the rock apart. This freeze-thaw cycle repeats countless times, breaking large rocks into smaller fragments. These fragments fall, tumbling down slopes, accumulating at the base of cliffs in piles called talus. Over time, gravity pulls them further downhill. Water, flowing in streams and rivers, carries the smaller pieces away. The streams carve channels into the mountainside, deepening and widening them with each rainstorm. Sediment is transported downhill, carried by the current, deposited when the water slows. Year after year, the mountain loses material, small amounts at first, but the losses accumulate over millions of years. Glaciers, when they form, are even more effective at erosion. Ice, when it accumulates to sufficient thickness, begins to flow under its own weight, moving slowly downhill like a river in extremely slow motion. As the glacier moves, it scrapes against the rock beneath it, plucking pieces free and grinding them into fine powder. The valley floor is carved deeper, the walls steepened. When the glacier eventually melts, it leaves behind a U-shaped valley, distinctly different from the V-shaped valleys carved by rivers. The Himalayas, the tallest mountains on Earth, are still rising. The collision between India and Asia that began around 50 million years ago continues today. The Indian plate is still moving northward, still pushing against the Eurasian plate, and the mountains continue to be lifted upward. But they are also being eroded. Rivers fed by monsoon rains and melting snow cut through the rock, carrying sediment down to the plains and eventually to the ocean. The balance between uplift and erosion determines the height of the mountains. If uplift is faster than erosion, the mountains grow. If erosion is faster, they shrink. In the Himalayas, uplift is currently faster, so the mountains are still growing taller. But the rate of growth is slow, measured in millimeters per year. The highest peak, Mount Everest, stands just under 9 kilometers above sea level. It gains a few millimeters in height each year, a change too small to notice in a human lifetime, but significant over geologic time. In 1,000,000 years, if the current rate continues and erosion doesn't accelerate, the mountain could be several kilometers taller. But erosion will accelerate as the mountains grow taller, because taller mountains catch more precipitation and experience more severe weathering. Eventually, the collision will end. India will stop moving northward, or the forces driving the collision will weaken. When that happens, the mountains will stop rising. Erosion will continue, unopposed, and the Himalayas will begin to shrink. This has happened to every mountain range that ever existed. The Appalachian Mountains, which formed around 300 million years ago during the assembly of Pangaea, were once as tall as the Himalayas. Now they are much lower, worn down by hundreds of millions of years of erosion. Their peaks are rounded, their valleys wide and gentle. The rock that is eroded from mountains doesn't disappear. It is transported, carried by rivers to lower elevations, deposited in floodplains, deltas, and eventually the ocean. Over time, these deposits build up in thick layers. The weight of the overlying material compresses the lower layers, squeezing out water and air, binding the particles together. Sedimentary rock forms, new layers recording the material that was worn away from higher ground. In this way, the rock that once stood as a mountain becomes the bedrock of a plain or the floor of an ocean basin. The cycle continues. If the sedimentary rock is buried deeply enough, heat and pressure transform it into metamorphic rock. If it is carried to a subduction zone, it may be dragged down into the mantle, melted, and eventually returned to the surface as magma. Or it may be caught up in a collision, compressed and uplifted, forming a new mountain range. The rock moves through a cycle, changing form, changing location, but never truly destroyed. This rock cycle has been operating for as long as the Earth has had a solid crust. It is driven by the heat of the planet's interior, by the motion of tectonic plates, and by the energy from the sun that drives weather and erosion. The cycle is slow, taking hundreds of millions of years to complete, but it is continuous. Every rock on the surface is part of this cycle, at some stage of formation, transformation, or destruction. Volcanic mountains form differently than mountains created by tectonic collision. They are built up by the accumulation of lava and ash erupted from below. Each eruption adds a new layer, and over time, the volcano grows taller. Some volcanoes erupt explosively, throwing ash and rock high into the air. Others erupt more gently, with lava flowing out and spreading across the surface. The type of eruption depends on the composition of the magma and the amount of gas dissolved in it. Shield volcanoes, like those in Hawaii, have gentle slopes and are built by the accumulation of thin, runny lava flows. These volcanoes can grow very large, covering vast areas, but they rise gradually. Stratovolcanoes, also called composite volcanoes, have steeper slopes and are built by alternating layers of lava and ash. These are the classic cone-shaped mountains, like Mount Fuji in Japan or Mount Rainier in the United States. They can grow quite tall, but they are also prone to collapse. The steep slopes are unstable, and landslides or explosive eruptions can remove large portions of the volcano in a single event. Volcanic eruptions are driven by magma rising from the mantle. The magma is less dense than the surrounding rock, so it rises, pushing its way toward the surface. If it reaches the surface, it erupts as lava. If it is trapped below the surface, it cools and solidifies, forming intrusive igneous rock. These intrusions can later be exposed by erosion as the overlying rock is worn away. Granite, a common type of intrusive rock, forms this way. It crystallizes slowly deep underground, and the slow cooling allows large crystals to grow, giving granite its coarse texture. Granite is often found in the cores of ancient mountain ranges. The mountains themselves have eroded away, but the granite that once formed the roots of the range remains, exposed at the surface. This granite is much older than the current landscape, a remnant of mountains that existed millions or hundreds of millions of years ago. By studying the age of granite and the structures within it, geologists can reconstruct the history of mountain building in a region identifying ancient collisions and rifts that have long since been obscured by subsequent events. Erosion is not uniform. Some rocks are more resistant than others. Granite, for example, erodes more slowly than sedimentary rocks like sandstone or shale. This differential erosion creates varied landscapes. Resistant rocks form ridges and peaks, while less resistant rocks erode into valleys. Over time, the landscape becomes a reflection of the underlying geology, with the patterns of rock types visible in the shapes of the hills and valleys. Rivers play a central role in shaping the landscape. They carve valleys, transport sediment, and redistribute material across the surface. A river begins as small streams high in the mountains, fed by rain and melting snow. These streams merge, growing larger as they flow downhill. The moving water has energy, and it uses that energy to erode the riverbed and banks, carrying particles of rock downstream. The amount of sediment a river can carry depends on the speed of the water. Fast-moving water can carry large particles, even boulders, tumbling them along the bottom. Slower water can only carry smaller particles, sand and silt, suspended in the current. When a river slows, perhaps as it enters a lake or reaches a flatter plain, it drops its sediment. The largest particles settle first, then the smaller ones, creating sorted layers. Over time, this deposited sediment builds up, forming deltas at the mouths of rivers or floodplains along their banks. Floods, though often destructive from a human perspective, are a natural part of the erosion and deposition process. When a river overflows its banks, it spreads water and sediment across the surrounding land. This replenishes the soil, depositing fresh nutrients and minerals. Floodplains are among the most fertile lands on Earth, and many early civilizations developed along rivers specifically because of the richness of these soils. Wind also contributes to erosion, though it is generally less powerful than water. In dry regions, where there is little vegetation to hold the soil in place, wind can pick up fine particles and carry them long distances. Sand grains, too heavy to be carried far, are pushed along the ground, saltating in short hops. Over time, wind can sculpt the landscape, creating sand dunes, wearing down exposed rocks, and polishing surfaces smooth. Deserts are shaped largely by wind and the occasional intense rainstorm. With little vegetation to protect the surface, erosion can be rapid during storms. Water rushes across the land, carving channels called arroyos or wadis, which remain dry most of the time. The sediment is deposited in alluvial fans, where the channels open onto flatter ground. Between storms, the wind takes over, rearranging the sand, shifting dunes across the landscape. Even in the absence of water and wind, erosion continues through chemical weathering. Rainwater, which is slightly acidic due to dissolved carbon dioxide, reacts with minerals in the rock, slowly dissolving them. Limestone, composed largely of calcium carbonate, is particularly susceptible to this type of weathering. Over time, rainwater can dissolve vast amounts of limestone, creating caves, sinkholes, and underground rivers. The landscapes formed by the dissolution of limestone are called karst, and they are found in many parts of the world. In caves, the dissolved minerals can precipitate out of the water, forming stalactites that hang from the ceiling and stalagmites that grow up from the floor. These formations grow extremely slowly, adding tiny amounts of mineral with each drop of water that passes through. Some stalactites have been growing for tens of thousands of years, recording in their layers subtle changes in the chemistry of the water and, indirectly, changes in the climate above. The landscape is never finished. It is always changing, responding to the forces of erosion and deposition, to the slow motion of tectonic plates, to the rise and fall of mountains. What exists today is a snapshot, a momentary configuration in a process that has no fixed endpoint. The mountains that seem so permanent will eventually wear away. The valleys will fill with sediment. New mountains will rise elsewhere. The cycle continues, driven by the planet's internal heat and the energy from the sun, reshaping the surface over and over across billions of years. The Earth settles into its rhythms, quiet patterns that repeat across timescales too vast to fully comprehend. Continents drift, mountains rise and fall, oceans open and close. These movements are so slow that they become invisible within a single human lifetime. Yet they are constant, driven by forces that have operated since the planet's crust first solidified. The ground beneath us is not static. It is part of a system in motion, a system that has been reshaping itself for over 4 billion years and will continue for billions more. Standing on solid ground, it is easy to feel that the Earth is unchanging, that the rocks and hills are permanent fixtures. But the story held within those rocks tells a different truth. Every stone has a history. It formed somewhere, perhaps deep underground or in the heart of a volcano. It was lifted by tectonic forces or deposited by ancient rivers. It has been weathered, broken down, transported, and perhaps reformed into something new. The rock remembers its journey, encoded in its minerals, its structure, its position within the layers of the Earth. The continents we live on are composites, assembled from fragments that collided and merged over hundreds of millions of years. Each fragment carries its own history, its own sequence of formations and transformations. When geologists map the rocks of a continent, they are reading a complex story written over immense spans of time. A story of oceans that no longer exist, mountains that have eroded away, and climates that have come and gone. The Appalachian Mountains in North America, worn and rounded, are the roots of a range that was once as imposing as the Himalayas. They formed during the collision that created Pangaea, when continents on either side of an ancient ocean were pushed together. The ocean closed, its floor crumpled and thrust upward, and the edges of the continents buckled, forming towering peaks. Those peaks have since been reduced by erosion, worn down by hundreds of millions of years of rain, wind, and ice. What remains are the deep foundations, the metamorphic rocks that were once buried far below the surface, now exposed by the removal of everything above them. In Scotland and Scandinavia, similar rocks tell the same story. These mountains, though separated by the Atlantic Ocean, were once part of the same range. They were connected before the ocean opened, before the rifting that would eventually split Pangaea began. The matching geology on either side of the Atlantic is one of the clearest pieces of evidence for continental drift, a confirmation that the continents were indeed once joined and have since moved apart. The same process that built those ancient mountains is still building the Himalayas today. The collision between India and Asia continues, though the pace is imperceptible without precise instruments. The forces involved are enormous, but they are applied so gradually that the crust responds by folding and thickening rather than shattering. Over millions of years, this slow compression has created the highest mountains on Earth and the vast Tibetan Plateau, a region where the crust is nearly twice as thick as normal. But the Himalayas will not last forever. Already, erosion is at work, carving deep valleys through the rock, carrying sediment down to the plains of India and Bangladesh. The rivers that drain the Himalayas are among the largest in the world, fed by monsoon rains and melting glaciers. They transport vast quantities of sediment, depositing it in deltas that are among the most fertile and densely populated regions on Earth. The material that once formed mountain peaks is now rich farmland, supporting millions of people. This is the nature of the Earth's surface. Nothing is permanent. Mountains rise and are worn down. Continents assemble and break apart. Rocks are formed, transformed, and reformed in an endless cycle. The timescale is so long that it defies intuition. But the processes are continuous, always operating, always reshaping the planet. Heat continues to escape from the Earth's interior, just as it has for billions of years. The planet formed hot, a mass of molten and semi-molten rock, and it has been cooling ever since. But the cooling is slow, and there is still immense heat trapped inside. Some of this heat is left over from the planet's formation. Some comes from the decay of radioactive elements, which release energy as they break down into more stable forms. This internal heat drives the convection currents in the mantle, which in turn drive the motion of tectonic plates. As long as the interior remains hot, the plates will continue to move. Continents will continue to drift. New oceans will open. Old ones will close. Supercontinents will assemble and break apart, repeating the cycle that has occurred at least several times in Earth's history. The exact configuration of the next supercontinent is uncertain, but the process itself is predictable. The forces that broke Pangaea apart are the same forces that will eventually bring the continents together again. Some geologists have attempted to predict the future configuration of the continents, projecting the current motions forward tens or hundreds of millions of years. These predictions are speculative, based on extrapolating current trends, but they offer a glimpse of what might come. In one scenario, the Atlantic continues to widen, while the Pacific continues to shrink. Eventually, the Pacific closes entirely, and the continents around it collide, forming a new supercontinent. This hypothetical landmass has been called Amasia. In another scenario, a new subduction zone forms in the Atlantic, and the ocean begins to close. The continents on either side move back toward each other, reforming a supercontinent in roughly the same position as Pangaea. This has been called Pangaea Proxima. Both scenarios are possible, and others are imaginable. The future is uncertain, shaped by processes that are complex and not fully understood. What is certain is that the continents will continue to move. the Atlantic is currently widening at a rate of about 2.5 centimeters per year. In 50 million years, it will be more than 1,000 kilometers wider than it is now. Africa is moving northward, closing the Mediterranean Sea. In tens of millions of years, the Mediterranean may disappear entirely, with Africa colliding with Europe and creating a new mountain range. Australia is drifting northward, approaching Southeast Asia. Eventually, it may collide with the Asian continent, adding to the complex geology of the region. These movements are slow, but they are relentless. The Earth's surface is never at rest. Even in places where there are no active volcanoes or earthquakes, the ground is moving, carried by the motion of the tectonic plate beneath it. This motion is so gradual that it requires precise measurements over many years to detect. But it is real. GPS satellites can track the movement of continents with remarkable accuracy, confirming what the geological record has long suggested. The surface of the Earth is shaped by the interplay of construction and destruction. Tectonic forces build mountains and create new crust. Erosion wears them down and redistributes the material. Neither process stops. They are in constant tension, and the landscape we see at any given moment is the result of this ongoing balance. In places where construction is faster, mountains are growing. In places where erosion is faster, the land is being lowered. Over the very long term, the balance may shift. As the Earth continues to cool, the heat-driving plate tectonics will gradually diminish. Millions or billions of years from now, the interior may cool enough that the convection currents in the mantle slow and eventually stop. When that happens, the plates will stop moving. Volcanoes will become less frequent. Mountain building will cease. The surface will gradually be worn flat by erosion, with no tectonic forces to renew it. But that future is unimaginably distant. For now, and for many millions of years to come, the Earth remains geologically active. The plates continue to move. Mountains continue to rise and erode. Oceans continue to open and close. The planet is alive, in a geological sense, constantly reshaping itself through the interplay of internal heat and external weathering. The rocks tell this story, if we know how to read them. Each layer, each fold, each fault line is a record of forces that acted in the past. Sedimentary layers record ancient seas and rivers. Metamorphic rocks record the heat and pressure of mountain building. Igneous rocks record volcanic activity and the cooling of magma. By studying these rocks, geologists can reconstruct the history of a region, piecing together the sequence of events that shaped it. This history is not always easy to read. The record is incomplete. Erosion removes evidence. Later events can obscure earlier ones. Rocks can be folded, faulted, and turned upside down by tectonic forces, making it difficult to determine the original sequence of layers. But with patience and careful observation, the story emerges. Each outcrop, each exposure of rock provides clues. When these clues are assembled, a picture of the past takes shape. The timescales involved can be difficult to grasp. 1,000,000 years is a length of time that exceeds human experience. 100 million years is incomprehensible. Yet these are the timescales on which the Earth's surface changes. Mountains take tens of millions of years to rise. Continents drift thousands of kilometers over hundreds of millions of years. The formation and breakup of a supercontinent takes 500 million years or more. Within these vast spans of time, there is room for countless smaller events. Ice ages come and go, each lasting tens of thousands of years. Sea levels rise and fall by hundreds of meters as ice sheets grow and melt. Rivers change course, carving new valleys and abandoning old ones. Volcanoes erupt, adding layers of ash and lava. Earthquakes rupture the crust, shifting the ground by meters in a matter of seconds. Each of these events is part of the larger story, a brief episode in the long history of the planet. The Earth is patient. It operates on its own time scale, indifferent to the brief lives of the organisms that inhabit its surface. A mountain does not hurry to rise. A continent does not rush to its destination. The processes unfold at their own pace, governed by the laws of physics and the available energy. There is no urgency, no deadline. The planet simply continues, moving through its cycles, reshaping itself over and over. For those who study the Earth, there is a certain comfort in this. The processes that shape the planet are knowable. They follow patterns that can be understood and predicted, at least in a general sense. The Earth is not random or chaotic. It is a system, complex but governed by rules. By learning those rules, by observing the evidence left in the rocks, we can understand not only what has happened, but why it happened. This understanding connects us to deep time, to the vast stretches of history that preceded us. The ground we stand on is ancient, shaped by forces that operated long before there were humans to witness them. The mountains we see, the valleys we walk through, the stones we pick up, all carry the marks of this long history. They are part of a story that is still being written, a story without an end, at least not one that is visible from where we stand now. The Earth continues. The continents drift, the mountains rise and erode, the rock cycles through its forms. It is a slow process, a quiet process, but it is always happening. The planet settles into its patterns, ancient and ongoing, a system in balance, constantly changing yet fundamentally stable. The surface shifts, but the underlying processes remain the same, repeating across billions of years, shaping the world we inhabit, creating the landscapes we move through, holding the history of the planet in layers of stone. The motion continues, even now, even in this moment. Beneath the surface, currents move through the mantle, slow and steady, carrying heat upward from deep within the earth. The plates respond, drifting across the surface at their unhurried pace, measured in fractions of inches each year. It is happening, always happening, though there is no sound, no visible sign of the movement. The ground feels solid, and it is solid, but it is also part of something larger, something that flows and shifts across timescales that stretch far beyond any single awareness. Mountains stand against the sky, their peaks worn smooth by time and weather. Rain falls on them still, as it has fallen for millions of years, seeping into cracks, freezing and thawing, loosening grains of rock that tumble downward. The streams carry these grains away, as they always have, adding to rivers that flow toward distant oceans. The process is gentle, repetitive, a rhythm that needs no observation to continue. The mountain does not notice its own erosion. The river does not count the grains it carries. The system simply proceeds, following patterns established long ago. Somewhere, a rift is widening, pulling apart at a pace too slow to measure without instruments. Magma rises into the gap, cooling into new rock, adding to the edges of separating plates. The ocean above grows slightly wider. Somewhere else, a plate is sinking beneath another, descending into the mantle where it will be heated and eventually melted, its material recycled into the Earth's interior. These movements balance each other, the creation of new crust matched by the destruction of old, maintaining an equilibrium that has persisted for billions of years. The continents rest on their plates, carried along without effort. They have been moving for as long as they have existed, drifting across the surface, sometimes alone, sometimes joined with others. They will continue this drifting, following the currents beneath them, tracing paths across the globe that will take millions of years to complete. There is no destination, no final position. There is only the movement itself, the ongoing process of drift and collision, separation and assembly. Rock lies exposed on hillsides, on cliffsides, in the beds of rivers. It holds its history quietly, the layers marking time, the minerals recording conditions that existed when the rock formed. Some of this rock was once deep underground, formed under pressure and heat. Some was deposited grain by grain in ancient seas. Some cooled from molten stone, solidifying as it reached the surface. Each piece of rock is part of the cycle, moving through its transformations at the pace the earth sets, neither hurrying nor pausing. The sky above changes with the hours, with the seasons, but the ground below changes on a different timescale entirely. What seems permanent in human time is temporary in geological time. What seems temporary in geological time is permanent in human time. These two perspectives exist alongside each other, neither contradicting the other, both true in their own measure. The Earth operates on its own schedule, and there is a steadiness in that, a reliability. Water flows downhill, following gravity, shaping the land as it goes. It has always flowed this way, carving valleys, depositing sediment, moving material from high places to low places. The patterns it creates are intricate, branching networks of streams and rivers, but the principle is simple. Water moves toward the lowest point it can reach, and in moving, it changes the landscape. The change is gradual, almost imperceptible, but it accumulates, layer by layer, year by year, shaping the surface into forms that reflect the passage of countless storms, countless seasons. The planet continues its work without audience or acknowledgement. There is no need for either. The processes that drive the Earth are self-sustaining, powered by internal heat and solar energy, guided by physical laws that do not change. Mountains will rise where plates collide. Erosion will wear them down. New rock will form from the sediment. The cycle will repeat as it has repeated, as it will continue to repeat, for as long as the Earth remains geologically active. There is a quietness to this understanding, a sense of scale that places individual moments within a much larger continuity. The Earth has been reshaping itself for billions of years. It will continue for billions more. The continents drift on, the mountains rise and fall, the rock cycles through its forms, and all of it happens in a rhythm so slow and so steady that it becomes a kind of stillness, a deep geological stillness that underlies everything, holding the surface together even as it slowly, endlessly changes.